Aloha, take-home exams going on. It's due Wednesday at 11-ish. So get it done. Do it before that. You will have to show your work. If you just put in the answers, that to me means you're cheating. You're gonna have to show me all your work for all those problems, or you'll lose those points for that part of the test. Let's continue on. You okay, Lord? Okay, let's continue on. So, diamonds spontaneously convert into graphite. Why do people buy diamonds? Any thoughts? It takes too long, right? So it'll be who looked it up last time? And how long was it? A couple billion years. So unless you live that long, then you have other things to worry about, probably. So feel confident in your diamond purchases. When the world gets crazy and money is no longer meaningful, will diamonds be worth something? Possibly. Who knows? So let's continue on. So, what is a spontaneous process? Spontaneous processes occur because they release energy from the system. Most spontaneous processes proceed from a system of higher potential energy to a system of lower potential energy, right? If we're walking down the stairs and we start to stumble, it's because we're going down and we don't like stumble. I'm just kidding. But in general, if we put a ball at the top of the stairs and it's on the slant or on the ramp, it's going to roll down because it's going from higher potential energy to lower potential energy, right? As it turns out, most spontaneous things are exothermic processes, right? So rusting of metal, that happens on its own, right? If you leave metal outside, it's going to rust. Do we have ways of keeping things from rusting? What's one way, Bryce? How can you keep something from rusting? If you have an old, nice car, do you leave it outside in the rain? Or what do you do if you want to keep it from rusting? Put it in a garage, put it in a cover and stuff like that. Um, but there are some spontaneous processes that proceed from a system of lower potential energy to a system of higher potential energy. So an endothermic reaction technically seems like it shouldn't happen, right? Like how could something absorb heat but it still be spontaneous? Can someone tell me an example of a endothermic spontaneous process? Feel free to read the board. Robert? So ice melting, do we have to put heat in for ice to melt? Yes, right? Ice doesn't release heat. It's not hot when ice melts, it's cold. So why is it that ice melting is spontaneous? Is it always spontaneous? Ice melting? Does ice always melt? Or opposite? Only when oh yeah, above, right? So if it's below the freezing point, it'll stay frozen like a piece of ice. If it's above it, it will melt. So the evaporation of liquid water to gaseous water is an example of this. Um, so when water evaporates, does it evaporate on its own? Yes, it does, right? If it was like a cold, really cold winter, does water evaporate on its own? I mean, it seems like water is always evaporating. The dissolution of sodium chloride in water, meaning when you dissolve salt in water, does that spontaneously happen? If you put salt in water, will it eventually dissolve on its own? For the most part, it will, right? That's also an endothermic process, but it happens spontaneously. So, how can something absorb potential energy yet have a net release of energy? Any thoughts on this? Any thoughts on how something could absorb potential energy yet have a net release of energy? Any thoughts? Show me some thought process. Hobie, what do you think? How can something absorb potential energy yet have a net release of energy? So if it's absorbing energy, that's what the heat is, right? It's absorbing heat. But how can it be a spontaneous process if it's endothermic? And we've talked about some examples of spontaneous endothermic things, right? So we know it does happen. So what could be a reason?
Like a lower temperature.
So it's going to have to do with this concept of entropy. Okay. So when a solid melts, the particles have more freedom of movement. Does everyone agree that a solid versus a liquid, which one is more structured? What do you think? Huh? The solid is more structured, right? Because a solid, like if you think of ice versus liquid water, ice has a fixed, structure and things like that. It's like it's shaped, whereas liquid can like have a lot of different things. So more freedom of motion increases the randomness of the system. When a system becomes more random, energy is released. We call this energy entropy. Anybody remember what letter we were going to give entropy? Nate, what letter was entropy? Take a guess. There's only 26 letters, and we know which ones are not it. Or, huh? E is energy. Good guess, though. That was a good guess. Yes, Emily? I don't see no S in entropy, but you're correct. It is S, okay? So entropy has a letter of S. Why is that? I don't know. I didn't invent it, okay? So melting is an endothermic process, yet ice will spontaneously melt above 0 degrees Celsius. More freedom of motion increases this, so we call this entropy because even though the heat is being absorbed, the molecules going from a solid to a liquid are becoming more random. So, what we're going to learn is the entropy, the overall entropy must be positive, or so if there's an overall positive entropy, that is going to dictate a spontaneous process. Okay. So, even though the absorbing of heat might be negative in most spontaneous processes, if the fact that you're going from a solid to a liquid is becoming more random, and so if you get a net gain in energy this way and a net loss this way, as long as the net gain is bigger than the net loss, you have an overall positive, right? So that's what we're going to be looking at in these cases. So water evaporating, this is also an endothermic reaction, right? We have to put in heat for water to evaporate. Is liquid water becoming gaseous water more random, Jack? Why? Because they don't have to be touching anymore. They're spread apart. They're moving around all crazy. So we can think of entropy as organization. Let me ask you this. Entropically speaking, is it more energy for you to keep your room clean or to keep your room messy? What do you think, Gabriel? Is more energy, right? Because everything has to be organized. Is there a lot of different ways your rooms can be messy? A lot of ways, right? So if we looked at most of us who room right now, how many of us have a very nice clean room? Anyone? I clean my living room because my wife was out of town, so that's the only time I clean the house is when she leaves. But then it turns into a state of entropy very soon after. The kitchen gets clean, and then my wife learns how to tear that kitchen up unbelievably. Okay. She thinks she cleans more, but I'm like, you make 5 times the mess. Like, I don't use like 7 different pans to cook something. I use the same pan over and over. Like, I clean it as I go because I don't want to clean 7 pans. But for her, she needs to get like a different thing to like mix something and a different thing to like, and it's like, dude, that's cool if you were like a chef and you have a bunch of people who clean up after you, right? So, like fancy chefs, they make all kinds of dishes because they never have to clean them. But when you have to like wash the dishes, you decide like, well, maybe I'm not gonna make that big of a mess. So there's two factors that determine whether a reaction is spontaneous. They're the enthalpy change and the entropy change. Okay. What was enthalpy's letter? Anybody remember? Emma? Very good. Enthalpy is H, which is heat. Entropy is S, which is, so this is heat, and this is this. order. Maybe that's what the S is from, right? Disorder, but that doesn't really make sense. We just ran out of letters, and that word's pretty close to energy and things like that, okay? So the enthalpy change is the difference in the sum of the internal energy and the pressure, volume, work energy of the reactants and products. That should ring a bell from Gen Chem A, but I'm joking when I say that. You don't even remember what we talked about on Friday, so how would I expect you to remember something from the year 2024, right? So delta H generally measured in kilojoules per mole, and in general, stronger bonds equals more stable molecules, okay? A reaction is generally exothermic if the bonds in the products are stronger than the bonds in the reactant. So someone tell me an exothermic reaction. Natalie? Mm-hmm. Very good. Piece of wood getting burnt, right? So, I mean, we can think of wood getting burnt. We can think of fossil fuels getting burnt, right? Why are fossil fuels one of the main things that we burn? Any thought on this, Jackson? They have lots of chemical potential energy, and how was that made? So usually like oil and things are found underground, right? And you have all this time where it's called fossil fuels. So fossils that are millions of years old that are like carbon and things like that get concentrated, compacted. That's great, but that's why we say fossil fuels are non-renewable. Technically, you could make more fossil fuels if you wanted. Why do we not make our own fossil fuels, Justin? I mean, we could do it fast. It would just be extremely expensive. And the amount of energy we put in to make those, we wouldn't be getting as much out. So there's no real reason to make fossil fuels, right? If it costs more energy to make them than what you're going to get out of them later. So so with the wood or with the fossil fuels, when they are formed, what is the product of a combustion reaction? Anybody know? Jack? CO2 and water, those have extremely stable, they're very stable, okay? So that's why when they are made, they're lower in energy, and that's why heat is released. Excuse me. Because since those carbon dioxide and water are lower in energy, it doesn't need that energy, so it releases it as heat. Okay? So an exothermic reaction means energy is released and delta H is negative. That's the take-home message for this. A reaction is generally endothermic if the bonds in the product are weaker than the bonds in the reactant. So what you need to know is endothermic reaction, energy is absorbed, and delta H is positive. Okay? So if you're not understanding all of this, the main thing you should understand is enthalpy is delta H. When it's positive, it's endothermic because it absorbs heat. When it's negative, it releases heat. So the enthalpy change is favorable for exothermic reactions and unfavorable for endothermic reactions. So that's basically telling us how could an endothermic reaction be spontaneous if a spontaneous reaction has less potential energy, right? So there are two factors that determine this, and it's the enthalpy change and the entropy change. So the enthalpy change is we can calculate using all the ways we learned in Gen Chem A. The entropy change we're learning about just now is the difference in randomness of the reactants compared to the products. So if I give you a couple situations, would you be able to tell me if that is so positive entropy, positive delta S means more random, negative delta S means less random, or more organized. Everybody comfortable with that? So let's try and look at a couple different things. So entropy is the measure of disorder. A positive entropy means a lot of disorder. Okay? So if we come in the classroom and we can sit anywhere we want, is that more disordered than if I made every single student fill in the front row from beginning to end? Which one's more ordered? Merve? Which one is that? So making everybody sit in a structured order is way more ordered, right? There is a little bit of variance. We could like adjust where we sit, but in general, when we're sitting everywhere, that's more disordered than everybody sitting in the front, right? So this guy named Boltzmann came up with a constant, which we might look at. Um, he came up with something that W is the number of energetically equivalent ways a system can exist, and random systems require less energy than ordered systems. So we're not going to worry about the Boltzmann constant. When salt, so this is an endothermic process. So if salt dissolving into water is endothermic, what must that mean about the entropy of salt dissolving in water? What's our thought on this, Cade? So if it's endothermic, that means it's losing energy, right? But if it's spontaneous, it has to have a net positive energy, right? So if we know the endothermic process is making the heat be not favorable, that must mean that the dissolving of the salt is a disorderable process, and it's disorderable in such a way that the amount of disorder outweighs the amount of endothermicity, if that makes sense. If that's a word, right? So salt, when it's solid, is pretty ordered, right? Like if you have a bunch of salt particles, it's just a bunch of white solid, right? Once it dissolves in the water, is it more or less ordered, Carissa? Less ordered, right? So the delta S is going to be positive, an increasing entropy. Going from a solid to aqueous will always be an entropically favorable reaction. Is that making sense? Ish. Let's look at so this is what like Boltzmann said. Let's say we had 4 gas particles. If we have 3 states, state A, state B, or state C, which one has the most possible combinations of this? What's our thought on this, Donovan? Hmm? So state C has more options. Is that what you're saying? That's everyone agree with that? If you have 4 particles and they're either all on the left side, there's only one way that can happen, right? Let's number these 1, 2, or let's use a different color. 1, 2, 3, and 4. The only way we can get 4 things on this one side is if all 4 are on there. This state C, does it have more options? Could we go 1, 2, 3, 4? Is that one option? Could we though do 1, 3, 2, 4? Is that another example of having 2 and 2? Is that different? The red and black writing. So does everyone agree that spreading out things is going to be more positive entropy than having it all clustered, right? It's like what I said, putting everybody in the front of the room. There's really only one way we can do that, and that's having everybody move to the front. Whereas when we move around, there's probably a million different combinations for the 15 of you in this class right now. And I'm just doing that for the recording. I know there's more than 15 of you. I just want to remember this someday when I never watch this video again. But what happens is you could also have number 2, 3, 1, and 4, right? You could have number 1 and 3 and no, let's not do 1 anymore. Let's do 2 and 4 and 1 and 3, right? So there's a bunch of different combinations with this. So basically, when we say macrostates versus microstates, that usually confuses people, but it just shows you there's 6 different situations where you could have 2 and 2, whereas there's only one combination where you have 4 and 0. Everybody agree with that? So there's more entropy having the 2 things spread out. Okay? So Entropy change is favorable when the result is a more random system, right? So delta S is positive in this case. Some changes that increase the entropy are as follows. Reactions whose products are in a more random state. So what is one way something can be in a more random state? Ian, what do you think? So if we're doing a chemical reaction, solids are more ordered than liquid and liquids are more ordered than gas. So if we're starting as a solid and it becomes a liquid, does everyone agree that this would be a positive or negative entropy? What do you think, Jessica? Positive, right? Because liquids are more disordered. What about sublimation, solid to gas? What would delta S be in this case, Angelina? Positive also. What about condensation? Liquid. Wait, what is condensation? Let's not do condensation. Let's do freezing. Liquid becoming a solid. What would this be, Bianca? Everybody see that this is negative because the solid is more ordered than the liquid, okay? So do we see how we can determine if something is positive or negative, okay? So there's going to be different, we're going to be able to quantify this eventually, but a lot of times we just want to see whether or not something is positive or negative. And sometimes, so if both things are positive, a positive plus a positive will always equal a positive. Everybody agree with that? A negative plus a negative will always equal a negative. So if the entropy is negative and the enthalpy is negative, that is always going to be negative, and that is always going to be a non-spontaneous process. If it's a exothermic process where delta H is negative, well, so that's a little confusing. So we'll look at that in a second. Reactions that have larger numbers of product molecules than reactant molecules. So if we're looking at a reaction where we have like 2A plus 1B makes 1A2B, would we say delta S is positive or negative? What would we think, Rebecca? So three things becoming one thing. Is that getting more disordered or more ordered? And more ordered is positive or negative? Negative. So this would be a negative delta S. Okay. If we looked at it in the reverse direction, one thing becoming three things, delta S in this case would be what, Janessa? One thing breaking down into three things, more ordered or less ordered? Less, one thing breaking down into three things, less ordered. So is that positive or negative entropy? Huh? Positive. Very good. Okay. When we have an increase in temperature, that's also going to make things more disordered. Does everyone agree that high temperatures are more random than low temperatures? If you think back to gas laws, high temperatures makes gas particles move faster. That's more disorder than cold temperatures where they're moving slower. Solids dissociating into ions upon dissolving will also have a positive entropy. So all of these situations are positive entropies. The reverses of these would be all what, Alondra? Positive or negative? If these are all positive, then the reverses of all these would be negative and getting more ordered. Okay? So for a process when the final condition is more random than the initial system, we say that delta S of the system is positive and the entropy change is favorable for the process to be spontaneous. For a process when the final condition is more ordered than the initial condition, we say delta S is negative. That's what we've been talking about. Remember this equation? Anybody remember this from 115A? Did we see something exactly like this, except a little bit different? It was delta heat of a reaction equals summation of N times the delta H of the products minus the summation of N delta H of reactants. Everybody remember that equation? Can you summarize what that meant, Cade?
It's just the overall entropy change.
Well, so when we use delta H, that was enthalpy in 115A, right? So if you look, so we could look up the enthalpy of different reactants and products. So this equation, this summation was confusing. All it meant was add up all the products and subtract all the reactants, their delta H's. And if it was positive, that told you it was an endothermic reaction. And if it was negative, it told you if it was an exothermic reaction. We can use this same equation by looking up the entropies of different reactants and products to determine if something has a positive or negative delta S, though we should be able to figure that out just by sometimes if we see that there's like more reactants than products or solids becoming liquids, things like that. So when materials change state, the number of macrostates changes as well. Things have more freedom. Solids have lower entropy than liquids, which have lower entropy than gases. Solids are more ordered than liquids, which are more ordered than gases. That all makes sense, right? So that's all this slide is saying. So let's do a conceptual exercise. Which of these three situations, A, B, or C, shows a positive entropy happening? Okay. I'm going to do a random check. And if we get it right, then the take-home exam is still due on Wednesday. If the person who I call gets it wrong, we're making the due date be tomorrow. Just kidding. Can't do that. But that'd be funny, huh? And the person who I randomly call is Donatella. Go. Yeah, don't do that. Know better. Which one has a positive delta S happening?
A.
Everybody agree with that? Anybody think something different? So having 4 and 2, is that more random than having 2, 2, and 2? Yes, probably right. Having 2, 2, and 2 going to all 6 and 1, that's way more ordered than having them all spread out, right? So we can definitely eliminate B. Having 1, 4, and 1 versus 2 and 4, that's basically moving one of these and putting it over there. That makes it more ordered, right? So this is also more ordered. So it should be a very good. Thank Donatella for the exam being the same time. And even if Donatella got it wrong, I would have still kept it the same. So, all right, let's do a couple more examples. Delta S is positive or negative in this situation. Avery, water, gas becoming water liquid. Is that a positive delta S or a negative delta S? Everyone agree? Anybody think that's a positive? Gas to liquid, that is a negative delta S. Delta S is negative. Very good. Um, let's see. Who else can we call on? Lucian, solid carbon dioxide subliming. You know what subliming is? Huh? Ask Nate. Anybody know what subliming means? Solid to gas. It's skipping the liquid phase. Solid to gas. Everybody agree with positive delta S? Delta S, not H. That is a positive delta S. Okay, 2 nitrogen dioxide gas becoming 2 nitrogen and an oxygen. Positive or negative delta S, Lowit? So you have 2 things becoming 3 things. What's more random, the 2 or the 3? The 3 is more random, and since it's a product, we would say that that is a delta S equals positive, okay? Let's do this one over here. The boiling of water. Robert. Boiling of water is what? Liquid to gas. That would be positive, I think. What about iodine gas becoming iodine solid? Anybody know what this phase change is called? It's called deposition. It's a random one. Kayla, what would it be? Everyone agree that it's negative? Last one, Ida. Calcium carbonate becoming calcium oxide and carbon dioxide. Everyone agree with that? Positive, negative, positive. That's what we had. For C, we said it was positive. This is the kind of stuff you can expect to see on your homework. The second law of thermodynamics states that the total entropy change of the universe must be positive for a process to be spontaneous. So, what we're going to see is a system. So, there's system and there's surroundings, right? We have our system and we have our surroundings. But the second law of thermodynamics is a law, a pretty strong indication that it doesn't have any exceptions. Yes or no? What do you think? So the law states that the total entropy change of the universe must be positive for a process to be spontaneous. My physics teacher in undergrad in 2000, he would have conventions trying to disprove the second law of thermodynamics. He was a physicist, so he was like probably one of my best teachers I ever had. He was like super smart and super cool. Um, he's the teacher who made me realize that homework is of paramount importance for a class. First semester physics, we had homework. My good friend in the class wouldn't do his homework. He got A's on every exam, but he got a B in the class because he got zeros on his homework. And the teacher's like, that's lame that someone who's like my strongest student gets a B. He should just give him an A. So the next semester, he made it so that we had no homework. And you know what that meant? I didn't do a single thing of homework and I didn't learn crap in that class. Okay. So the take home message is if you're not working on the material, you're definitely not going to be able to, like, you have to like have repetition and do things to understand it. So that's one of the reasons I got homework. I'm pretty sure I got like C's and D's on all the tests, but he gave me a B in the class because one time I shouted out an answer and he thought it was like so amazing that someone knew it. And I was like, I just always shouted out stuff because I don't know if you knew, but you know all the people in this class who shout out stuff? Oh, no one? That's how I was, okay? Whenever the teacher would ask a question and it was crickets, Donatella, you sometimes say stuff. Thank you very much, okay? But in general, I would just always shout out answers. And a lot of the time they were wrong. But because of that, he thought I was like so smart. And like, I was like, I just like yelling stuff, you know, like I didn't give a crap. Like I didn't pay attention. And honestly, I was able to pass that class and I really don't know anything about electricity and magnetism in physics. Anybody take that second semester physics yet? No. When you get there, it'll be fun and then you can know more in that subject than me. Okay? So we have system and surroundings. What this law states that the universe for a process to be spontaneous. So could something have a system where the entropy goes down and still be spontaneous based on this formula right here, Jessica? So spontaneous process must mean that the delta S of the universe is positive. That's what the second law is stating, right? If the delta S of the system that we're talking about has a negative entropy, could it be spontaneous even though it has a negative delta S system, Jessica? What do you think? Exactly. So, just like we said, exothermic reactions are usually spontaneous and endothermic are usually non-spontaneous, but there are situations because in those situations the entropy outweighs the negative enthalpy. So in this case, if a system has a delta S that's negative if it's causing its surroundings to be, so even though we're getting more organized, right? That is a very negative delta S. Does everybody agree with that? So like in our bodies, do we synthesize proteins and stuff like that? Yes or no? And would that be entropically favorable, Abri? To generate, so taking all these different amino acids and stuff and making it into this super complicated, structured protein. What would the entropy of that be? Nope. Very negative, right? You're taking a bunch of random amino acids that could be in any order, and we're putting it into this super complicated thing. But can we do that? The answer is yes. How can we do that? We will learn about that in a second. So we'll look at this. If the entropy of the system decreases, then the entropy of the surroundings must increase by a larger amount for that actual thing to be spontaneous. When the delta S of the system is negative, the delta S of the surroundings must be positive and big for the reaction to be spontaneous. Okay, so let's go ahead and continue on. So the delta S of the universe is equal to the delta S of the surroundings and the delta S of the plus the delta S of the system. So when ice is placed in water, heat flows from the water into the ice. According to the second law, heat must flow from water to ice because it results in more dispersal of heat. Dispersal. The entropy of the universe therefore increases. So that's weird. So going from a solid to a liquid. So what are we saying? When ice is placed in water, heat flows from the water to the ice. According to the second law, heat must flow from the water to the ice. So heat flows from the water into the ice, and that's how it melts, right? We all agree that the more ice you put in something, the longer it stays cold. Does it get colder though? Because of what? I mean, we talked about that early on in this semester, right? We said ice water is always the same temperature. How do we make ice water colder? Jack, how do we make it colder? If you add salt to it, remember you can make like homemade ice cream and stuff. So the second law demands that the entropy of the universe increase for a spontaneous process. Yeah, processes like water vapor condensing are spontaneous, even though the water vapor is more random than the liquid water. If a process is spontaneous, yet the entropy change of the process is unfavorable, there must have been a large increase in the entropy of the surroundings. So the entropy increase must come from heat released by the system, and the product must be exothermic. So in this case, is the delta S of the universe positive? So as long as the delta S of the surroundings has a more, so if we measure this, let's just say that this was 3.5 centimeters, and this goes down by 3 centimeters, do we still see that we have a net positive half centimeter? So even though the system has a negative delta S, which is non-favorable because it is getting more ordered, as long as the surroundings, when that happens, is getting more disordered and it happens more so, then that's going to be the case, right? So let's go ahead and take a look at it. When a system process is exothermic, it adds heat to the surroundings, increasing the entropy of the surroundings. So we said that exothermic processes are generally going to be spontaneous, right? And that makes sense in terms of enthalpy because a spontaneous process does, I mean, an exothermic process does what, Nana? It adds heat to the surroundings, right? So if my process is exothermic and it heats up all of the stuff around it, is all of the surroundings around it getting more disordered? Yes or no? Natalia? When heat is generated, does that increase the entropy of the surroundings? Yes, it does, right? So that's why we say most exothermic processes are usually um, going to be spontaneous. When a system process is endothermic, it takes heat from the surroundings, decreasing the entropy of the surroundings, right? So in those cases, most endothermic processes should be non-spontaneous. The amount of entropy of the surroundings changes depends on its original temperature. The higher the original temperature, the less effect addition or removal of heat has. So if it's already hot, when something releases heat into a hot system, do you notice it? If it's a hot day, right? Let's say it's in the middle of summer and it's 110 degrees in Sonoma. It hasn't been like that for a while, but it used to be like that, okay? If you turn on a heater on a hot day, is that going to make any difference in the world other than wasting energy? Not really, right? But when it's a cold day, does turning on the heater, do you feel an effect on that? For sure, right? So an exothermic process increases the entropy of the surroundings. An endothermic process decreases the entropy of the surroundings. That is something we can write in whatever you want to write in that's permanent, okay? So when does water freeze spontaneously? Angelina, when does water freeze spontaneously? When it's cold, right? When it's below what temperature? 0 degrees Celsius, okay? So what happens is the second law states for any spontaneous process, the entropy of the universe increases. So at a temperature, so when does water freeze spontaneously, Bryce? -10? Yes? So water freezing at low temperatures. Does water freeze at low temperatures? So is liquid water becoming solid water, is that a positive entropy or a negative entropy, Emma? Liquid becoming solid. That is correct. Delta S is negative. Why is this negative? Anyone know? Because it's more structured, right? So the delta S of the system, the water, is going down. It's a negative entropy. Does everybody see that? But what happens is the delta S of the surroundings is more positive. So did we say this is endothermic or exothermic? So what is this? This got to be exothermic, right? Because melting ice is what? Exothermic or endothermic? Do you have to add heat to melt ice or does it absorb heat to melt ice? It absorbs heat, right? To melt ice. So to freeze ice, that must mean it is a exothermic process. So because it's an exothermic process, is it going to heat up its surroundings when it releases heat? Yes. So at temperatures below 0, the amount of heat that it releases is more than the amount of negative disorder that is happening, right? So the water will freeze. When the temperature is high temperature, it's still a negative delta S, right? So that's going down. But at high temperatures, as I said, if you put a heater next to your feet in the middle of summer, does that give you any like true effect? Not really, right? So at high temperatures, the amount of temperature that the surroundings is increasing, it was already hot. So adding a little bit more heat only boosts up the delta S a tiny bit. So the net delta S of the universe is negative. And what do we see? Water does not freeze above 0 degrees Celsius. Everybody see that? So some things to note down. When something happens above a temperature and has a different thing below a certain temperature, this would be like freezing point or melting point of something, right? That's because on one situation, the amount that it changes the surroundings is more than the amount that it changes the system. But above that temperature, the amount that the surroundings increases is less than the amount that the system goes down. So it gives a net negative. Everybody see that? So in these situations, we have a temperature which is like a melting point or a freezing point. Above that temperature, it melts. Below that temperature, it doesn't melt, right? That's what, so like what is some, like if you want to heat up a metal, you have to heat it up to a certain high temperature for it to melt, right? That is only going to happen because it's going to make it the delta S change. So you'll see this. So in this case, the release of heat energy by the system disperses the energy into the surroundings, increasing the entropy of the surroundings. The delta S of the surroundings is greater than the amount of negative delta S of the system. Therefore, it's spontaneous. In this one, the release of heat energy by the system disperses that energy into the surroundings, but it only goes up a little bit. This goes down more. So this is non-spontaneous. So we're going to take all this into play. So when heat is added to the surroundings that are cool, it has more of an effect on the entropy than it would have if the surroundings were already hot. That makes sense, right? Water freezes below zero because the heat released on freezing increases the entropy of the surroundings enough to make the delta S of the universe overall positive. Above zero, the increase in entropy of the surroundings is not enough to override the amount of entropy of the system becoming a solid from a liquid. So that is why that is. So when we have something that is positive at some temperatures, or when it's spontaneous at some and not others, the delta S of the system is always negative. It's positive and large at low temperatures, positive and small. So we're going to be doing this over the next couple days. So to summarize all of these heating changes and entropy, a process that emits heat into the surroundings. Q of the system is negative. So Q is just another way to think of heat, right? Q and delta H are kind of interchangeable. It increases the entropy of the surroundings, therefore giving us a positive delta S. So exothermic gives positive delta S to the surroundings. Everybody see that? A process that absorbs heat from the surroundings decreases the entropy of the surroundings. So an endothermic reaction is going to give us a negative delta S of the surroundings because it actually cools down the surroundings. When things cool down, they don't move as fast. Temperature goes down. The magnitude of the change in entropy of the surroundings is proportional to the magnitude of the Q of the system. I don't know what that means. So there's a formula for this, the delta S of the surroundings. I don't think we need to know this. How would we, so let's try and do one quick problem before we end the day. Calculate the entropy change in the surroundings associated with this reaction occurring at 25 degrees Celsius. So is this reaction going to have a delta S surrounding positive or negative? Robert? Yep. So what does that do to the surroundings?
That would make it. No, negative.
That would be delta H is negative, but delta S, when I heat up so when I release heat, am I going to increase the temperature of the surroundings or decrease the temperature of the surroundings when I'm releasing heat? You're going to increase that temperature of the surroundings, right? Does that increased temperature have a positive entropy or a negative entropy? Things moving faster, that's more positive. So this would be a positive delta S. Determine the sign of the entropy change for the system. So we had one thing plus five things, making three things plus four things. So one plus five makes 3 plus 4. Bryce, is that a positive delta S or a negative delta S? So this would have a delta S system is positive. Everybody agree with that? So is this reaction always spontaneous, sometimes spontaneous, or never spontaneous? Kayla? Everybody agree that when both the delta S surrounding and system are positive, the delta S of the universe will always be positive. This reaction will be spontaneous at all temperatures and things like that. Okay? It's only when these things are different do we have a temperature change. If both of these were negative, that would mean what, Nana? So when these are both positive, delta S universe is always going to be positive and it's always going to be spontaneous. If, for example, we had this was negative and this was negative, doesn't that mean that the delta S of universe will always be negative and that reaction will always be non-spontaneous? Now, if one is positive and another one is negative, now we have to look at the temperature and see, does the positive outweigh the negative or the negative outweigh the positive? Everybody see what we're doing here? So we're trying to figure out if a reaction is spontaneous or not, and we'll do that. We'll continue this next time. So that was positive, that was positive. When they're both always positive, the reaction will always be spontaneous. Make sure you get your exam done and no cheating. Okay. I looked at some people who turned it in, and I'm just kidding. I didn't look at anything. I don't look at anything till it's all turned in. Aloha.